Greetings and welcome to the video on how we can use tables and graphs to represent linear equations. So this is from Chapter 8, Lesson 2, and in this video we're going to be talking about independent variables, dependent variables, and then how we can use linear equations and graphs to show solutions to an equation and analyze the relationship between some two quantities. So when we get into this, an independent variable, that is the variable or the quantity that does not rely on anything else. And this is something where if you're talking about like how far you travel at a certain speed, your independent variable would be something like I drove for 2 hours. So the amount of distance you drive is based on the amount of time that you drive. So this is the thing, quantity does not rely, or it does not rely on anything, and it's used to calculate other things, other info. And that other info is specifically called the dependent variable. So the dependent variable is, it depends on the independent variable. So depending on what your independent variable is, that's going to impact the value of your dependent variable. So let's look at this. We'll identify those as we go through it and see kind of how those things play out. So the width of a rectangular length is 2 meters less than its length. So if we have a tank here like this, we know that its width here, or here's the length, and the width on this side is going to be 2 meters less than its length, or the length minus 2. So if the length is p, well, that seems ridiculous that the length would be p and not. I'm going to change that. Length is L and W, the width is W. We're going to be writing an equation to express our width in terms of our length. And so this is going to be key for us here, is in terms of what? Writing an equation, blah, blah, blah. So we are going to be, first off, writing an equation that describes the length. So because we're describing the length, or I'm sorry, describing the width, so we are looking for the width. That must mean that it's going to depend on the length. Or as the length changes, W will also change. So that then tells us that our independent and our dependent, well, our dependent is going to be W because it is based on the length. So our independent is length. Let's write an equation that captures this, that talks about this. Let me move this stuff out of the way. So we are trying to find W. So that means that our equation is going to be W equals something, because we are looking for the value of W. So we want to make that variable what is all by itself, it's isolated, and it's equal to something. And we know from over here and from the problem that our width is the same as the length minus 2. So if we're going to complete this table, just to check and see, I'm just going to imagine, what if I say that our length is going to be 10 meters? So our width then, if we know our width is 2 less than that, our width should be 8. So I'm going to quick check and see. Our picture tells us that our width is going to be 8, but let's check with our equation. So if I substitute a 10 for L, and then we do some calculating, W must equal 8. I'll check it out. So that makes me feel like this equation is good. Now what's different about this from the equations that we looked at in lesson 1 was that we have 2 unknown values here. And so we need to be plugging in values for one of those variables to help us find the other one, because we can't solve it otherwise. So if we look at this table on the bottom, we have a bunch of variables or a bunch of values for our length. And so these are independent because we are picking those. We're deciding this is the value, and we're putting that in, and it's going to tell us what our width is going to be. The width of our tank is going to depend on the length that we build it. So they gave us a couple of them. So if we put a 3 in there, our width is going to equal 3 minus 2, so width equals 1. Awesome. Width will equal, let's say our length is 4 minus 2. So our width is going to be equal to 2. What if our width is 5? 5 minus 2 is 3. So our width is going to be 3. And then, as you notice, we do have a pattern here, so that would be 5, and that would be 6. So now we've taken this problem, we did a quick little picture, captured that with algebra, and now we're substituting a value for our independent variable. So we sub value of independent to get the dependent. Once we have that, now we can do some graphing. We can plot the points. So when our length was 1, our width was 3. When our length is, I'm sorry, I flip-flopped that. Apologies. When our length was 3, our width was 1. When our length was 4, our width was 2. 5, it was 3. 6, it was 4. 7. Now I could keep going forever and ever. And so I'm going to connect these and draw a line with an arrow because we could keep going. Our lengths could keep getting bigger and bigger and bigger, and it would never stop. But they would still be dimensions of that tank. This relationship would work out. So now that we have plotted this, it seems to me like we can say that our independent is going to be our x-axis. So when we are graphing, our x-axis is our independent variable. And our y-axis is our dependent variable. So we picked a length, and that told us what the width would be. And so the value in using these graphs is it allows us to show all of the solutions to a problem. If, let's say, we only plotted when our length was whole numbers, 3, 4, 5, 6. Well, what if it was 6.5? That means we could look and find on that line, if our length is 6.5, according to this line, our width is going to be 4.5. Or if it was, let's say, 5 1/4, our width is going to be 3 1/4. So by graphing, we are showing all the solutions. Graphs show all solutions. Oh my gosh. It allows us to look at this relationship between the length and the width and see how are they related. Oh, as the length increases, the width also increases. Pretty great. And we could look at another problem with this, so why don't you take a moment, you could pause it, do this same problem, and then come back. All right. So, writing an equation, it looks like if we have 1 can of paint, it contains 5 gallons, and let's see, C represents the number of cans, and V is the volume. So our total volume is going to equal, well, this one's 5, and then we don't know how many cans we have. But we do know that each one is 5. So it looks like our volume equals 5 times C. Oh, but that's not how we write algebra. We would write it as volume equals 5C. And this seems to make sense. If we had 1 can and we substituted that in there, we would have 5 gallons. So V would equal 5 times 1. V equals 5. Hey, check it out. It does work. So we can pick any number of cans that we want. We'll just do 1, 2, 3, 4. I'm just going to pick 6 then. And I know that if I am substituting and solving, my volume is going to equal 5C. And again, if you notice, this here, the variable by itself is our dependent variable because its value depends on the calculation that we do on the right side. So 1 times 5 is 5, 2 times 5 is 10, 3 times 5 is 15, 4 times 5 is 20, 6 times 5 is 30. So our independent, the number of cans. If we have 1 can, we get 5 gallons. 2 cans is 10, 3 cans is 15, 4 cans is 20, and 6 cans is 30. So if I have 0 cans, I would have 0 gallons of paint then. And this could continue if I bought out all of the paint that there was ever at the store. So to quick check ourselves, we didn't on our table include 5 cans of paint, but according to this graph, the solution for 5 cans of paint is 25 gallons. And if we were to substitute 5 times 5 cans, we would get 25 gallons. So our graph helped us see that, and it helped us analyze that relationship.